Hello and welcome. Let's get comfortable. Today we'll be looking into curve V1 and V2. That's the stable swap and crypto swap. Now, there have been some integrations, some spin-offs from this that have gone not so well. There are a few public available reports you can get to check out. Some persons try to re-engineer curve, maybe in Rust in a whole different language, or they just choose to make their own implementation of this. And there were some fails. Some were epic fails, but thankfully they were found and corrected just in time. Today we're going to look into a few of these things, and I'd like you to walk with me. So Curve is it's a DeFi protocol. It's one of the oldest and has been around for quite a while. You would enjoy very, very low fees when swapping stablecoins, especially. I got to learn this practically. And I was wondering to myself, how did I spend 2, 3, 4% on transaction fees on Uniswap when I could have gotten the same thing done on Curve for a fraction of that amount? That's swapping stables to stables, maybe USDC to USDT or DAI to USDC. But all of these protocols, in as much as they try to help you maximize profits, they help you maximize limit your exposure rather, while providing that flexibility of use. Some things inherently in their design might be a little tricky for users to get to understand. So if you're a protocol developer, if you're simply a person looking to learn a little more about some security, think of this like a checklist, some security features to get to keep in mind, especially when working with Curve V1, then you should get to watch this at the very end. The first thing we're going to look at is the decimals. It goes without saying, one of the most exploited things in DeFi protocols, especially when you're integrating tokens with your protocol. Say, for example, USDC on a certain chain might have 6 decimals, and on another chain, you're looking at 18 decimals. But now with Curve, this is it's even more tightly knit because it's math heavy. So all of this math would be affected if the decimals are off. And in Curve, thankfully, there is a function called the XP function. Call X the token and P precision, that helps you adjust the tokens to swap by multiplying or dividing by a certain number of decimal places. So say 1E18, for example, or 1E6, it will be scaled up all the way to 1E36 and then used in the same basket as other tokens together. Something else to note is that imbalance fees exist. Now, imbalance fees you should get to pay this when your swap is completely skewing the pool. It's adjusting it a certain way. So say, for example, you have 10,000 USDC and 10,000 USDT and 10,000 DAI all together in the same pool. So that's 3 stable coins pulling together to make about $30,000 of value. That's what you could term the liquidity or the D value. Now, when you have all of that together and you try to make a swap, or you try to add liquidity rather, say you add liquidity into USDC, you add $2,000 worth of USDC, the pool now becomes imbalanced because you have 12,000 USDC, but still have 10,000 USDT and DAI. When this happens, it would slightly adjust the pool's value, but also the token's individual weight in that pool. Now, to get to avoid this, especially when adding or removing liquidity, Curve gets to charge you a fee, and it's called the imbalance fee. And this fee is used to offset that shift in the pool's already existing balance, because these things are meant to be together in a pool relatively equal. Number 3 is okay. This is nice too. It's for calculating the virtual price. Now, virtual prices, especially in Curve, are calculated by utilizing the D value, that's the liquidity, the number of tokens, as well as the precision. So the formula should be D multiplied by P divided by the total number of tokens available. And this is used to determine the price per token. So if you have this, would now be more in a uh, multi-token swap, not a stable coin, for example. If say for example you have 4 tokens in your pool, maybe that's Uni, Ethereum, you have DAI, and possibly Bitcoin, all in one pool. The virtual prices will be calculated based on all of those tokens together, not just one or two of them. So say you want to make a swap between USDC and BTC. If only those 2 tokens are factored into the calculations and you don't get to adjust for the other 2 tokens, that's Ethereum and Unia, then you would be making very, very, very wrong calculations concerning that price. So these values they should be all held together. So you're thinking, if I am working on this pool and there are 4 tokens in that pool, then everything I do, every calculation I make, every little bit of math that goes on should factor that token in as well. This would lead to something really interesting because we'll talk about the hack a little later. Let's see. Number 5, malfunctioning reentrancy locks. Now, this was a hack from about 3 years ago, and over $60 million was lost here. That's a lot of money. Compared to the Bybit hack, which was around 1.4, 1.5 billion, it doesn't look like it's so large, but that is still a large amount of money, to be honest, to be lost. So that could have been your funds, could have been, I had no funds locked in Curve as at then, so hopefully we don't get caught, but stay protected. What happened here was that the version of Viper was the issue. So Viper released the 0.3.1. It was a breaking change. Yes, that's what was pushed. But within the earlier deployed contracts, there was a bug that was sitting still, just waiting to be exploited. And the attacker found this out. Here's what the attacker did. When they realized this, they made sure to take flash loans. And from flash loans, they interacted with the affected pools, because these pools were deployed using the previous versions, the earlier versions of Viper, 0.2.15, 0.2.16, 0.3.0, and it was crazy. The total of 4 pools were exploited, and I think the Try Crypto pool was also vulnerable. But thankfully, during the middle of this, there was also a recovery going on alongside. So while the attacker did try to drain the protocol completely, they couldn't get to do that. Now, the vulnerability here was because of the reentrancy locks. So in earlier versions of Curve that utilized those earlier versions of Viper at those pools, the reentrancy lock was not stable. It was something that you'd say affected the storage layout. You'd store the mutex in this slot, and then it is unavailable to be read when called again. Now, this won't have looked like much of an issue with the code itself, or in how the bytecode was decompiled from code and then read by the compiler. Now, it's fixed now, but if you're working with Viper versions that are much earlier than 0.3.1, then you should get to know that this could be a very sizable vulnerability. The next The next issue here, issue number 6, is to accommodate as many tokens as used. Okay, I did get to explain a bit of this earlier when I mentioned that your calculations, your adjustment should get to factor in for each of these tokens. So say it's DAI, for example, or USDC or ETH, all put together in one pool. Anytime there are calculations to be made, anytime there are swaps to happen, anytime there's even anything that occurs with just one token or 2 out of n tokens in that pool, they should all be factored in together in the same calculations. Number 7 here is swap fees. Okay. Now, imagine you could get to add and remove liquidity for a cost that was much less than for swapping tokens. Say, for example, it costs you 0.15% to swap a token. And on the other hand, it costs 0.05% to add liquidity to a pool and then remove the other token instead. You'd probably choose that because you'll be to cost you say 0.05% less than a single swap. Now that happens only because fees are not added. Say you get to skew the pool, you get to pour in $1 million USDC into a $10 USDT pool. So previously it was 10 USDC to 10 USDT, and then you poured in $1 million USDC. Effectively, you've made USDT 0.000, a really small percentage of that pool value, and then it's imbalanced. If swap fees were charged on every swap deposit, every addition of liquidity or removal of liquidity, then you would be mitigating this to a great extent, knowing that you won't get to imbalance the pool so much for someone else who will be coming in. Now, this is much worse with a, let's say, multi-token pool that's not stables, because now you're able to control in a very big way. This will cost you a little maybe on slippage though, but then you're paying no fees when you're swapping, when you're imbalancing the pool. So for front-running attacks, for those attacks where it's possible to grief the user who comes after you and then back run, so that's basically a sandwich attack, this would be a heaven for them, because there'll be no fees charged for these kind of imbalances. And the last but not least, you could just put these two together. That's for slippage. Considering the D value, it's denoted as liquidity in the original Curve V1 docs. And then the A value, which is the amplification factor, it affects the straightness or the curvature of the graph when you get to look at it. I think we could get to pull that up here. Let's see what the graph looks like. It is very interesting to see though. Now, say you have slippage. For slippage tolerance, you expect a certain amount of funds to be released or to be sent back to you when you make a swap. Same for LP tokens as well. So say you're swapping 10 USDC to Ethereum, you have a minimum amount of Ethereum you'd like to receive, or you want to swap 1 ETH to 4,000 or 4,300 USDC. And you say the least you want to receive back should be 4,290. That's your minimum amount out. So it means if the price gets to bounce between 4.3 and 4,290, you're cool with it, so long as it doesn't go below 4,290. So just give me 4,290. Now, for slippage, when the tolerance isn't rightly set, you could be exposing yourself to losing a whole lot more. So in Uniswap V2, for example, V2, V3, V4, the minimum amount out variable is recommended to not be set to 0. especially because if it is set to 0, it means that your swap will be executed at the worst price possible with no restraints. Now here, if you're setting your slippage tolerance values to anything at all that is not properly checked, then you could be losing out on that swap even though you think you're protected. So say, for example, you're setting the tolerance to the pool ratio, and the pool ratio is compared to a different value. So let's say for the swap to execute, you have three things you get to check. And of all these three things, the most important to you is that there will be a significant closure between how much you started with and how much you're ending with. So say 1.0 to 1.1, 1.0 to 1.01, you're expecting that there's not so much of a difference between these values. But then you're checking out the wrong things, you could get into a bit of trouble. So a practical example of this is in the Mantra DAO. Yes, Mantra DAO got to do an audit with Code Arena, and this finding was one of the high severity findings where the pool ratio and the deposit ratio were to be checked, but then the difference wasn't accounted for with slippage. So how this works is that when you make a deposit into the pool, when you get to adjust the pool value, the initial amount and the final amount are checked and put into a ratio. The same for deposits. When you get to deposit the value, the initial deposit and the final deposit will be checked, set into a ratio. Now, from that deposit ratio, from the pool ratio, your tolerance could be calculated. But now, if you're banking on just one of those things and not the both of them, the difference between them is where you should expect that is checked, not the other way around, not individually.